Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. Today's lecture, I'll be teaching two transistor analogy, UJT firing circuits. And this is two transistor analogy. If you see, this is the structure of the SCR. This is the structure of the SCR. And if we can bisect this SCR into two halves, in that case, we can analyze two transistor model. The moment when we are actually bisecting this particular thyristor, in that case, junction J2, J1 and J2, it forms PNP transistor, and junction J2, J3, it forms NPN transistor. It forms two transistors, and in order to analyze the operation of thyristor, we need two transistor analogy. And here, for that purpose, let us obtain the expression for two transistor analogy. And here, let us take the general equation of a transistor where IC is equal to alpha IE plus ICB naught. This is the general equation of any transistor. And let us consider for the transistor 1. Here, for transistor 1, the equation transforms into IC1 is equal to alpha 1 IE1 plus ICB naught 1, where alpha is the current gain of the transistor, IE is the emitter current of the transistor, ICB naught is nothing but the collector to base leakage current. And here, there is the, and let me substitute here, IE1 is equal to IA. IE1 is equal to IA. That is because here anode current is which is flowing through the emitter of the transistor 1. So that is the reason here I have considered substituting this equation in the above equation. We get IC1 is equal to alpha 1 IA plus ICB naught 1. And this is the equation 1. Now, let us apply KCL to transistor 1. Applying KCL to transistor 1. We get here IE1 is equal to IB1 plus IC1. And here IB1 is equal to, we can also write IB1 is equal to IC2. If you see, the transistor base current of the transistor 1 is what flowing through the collector terminal of the transistor 2. That is the reason here we take IB1 is equal to IC2. And here if you see, the first equation is concerned, emitter current of the transistor 1, it is equal to the summation of base current of the transistor 1 and collector current of the transistor 1. So that is how we have got these two equations. And let me substitute in IE1 this equation in the above equation. We get IE1 is equal to IC1 plus IC2, where we already have IE is equal to IA. Let me substitute IA1 is equal to IA, which is equal to IC1 plus IC2. And this is equation 2. This is one of the very important equations. And now, for T2, let us write the equations for transistor 2. In that case, if you see, here, collector current 2 is given by the formula alpha 2 IE2 plus ICB naught. And if you see here, emitter current is equal to that of the cathode current. So let me write IE2 is equal to IK And if I substitute this in the above equation, we get IC2 is equal to alpha 2 into IK plus ICB02. And this is equation 3. And let us apply KCL. Let us apply KCL for the transistor 2. Applying KCL to the transistor 2. In that case, we get IC2, IE2 is equal to, it is a summation of IB2 and IC2. Summation of IB2 and IC2. Where the IB2, base current of the transistor 2, is equal to that of IC1 plus IG. IB2 is equal to IC1 plus IG. And from this, we can write IE2 is equal to, let me substitute the value of IB2 in this particular equation. In that case, I get IC1 plus IC2 plus IG. And if you see in the previous equation, we have seen IA1 is equal to, IA is equal to IC1 plus IC2. And let me substitute this here. In that case, we get IE2 is equal to IA plus IG. Where IE2 is nothing but IA. And now, here, we can also write IE2 is nothing but IK, which is equal to IA plus IG. And now, let me substitute equation 1 and 3 in equation 2. In that case, we get IA is equal to, what was IC1? IC1 was alpha 1, IE1 plus, or we can also write this as IA. Alpha 1 IA plus ICB01 plus IC2 is equal to, we have got alpha 2 IK plus ICB02. Here, alpha 1 into IA plus ICB01, where IK is equal to, here I am substituting this equation IA plus IG. IA plus IG. In that case, we get ICB02, which is equal to IA. And now, let me take IA terms to the left hand side, and my aim is in order to obtain the value of IA. So here, IA is IA minus alpha 1 IA minus alpha 2 IA is equal to alpha 2 IG plus ICB01 plus ICB02. Here, let me take IA common on the left hand side. In that case, 1 minus, I get alpha 1 plus alpha 2, which is equal to alpha 2 IG, same thing, ICB01 plus ICB02. And as I said, my aim is in order to obtain IA, which is equal to alpha 2 IG plus ICB01 plus ICB02 divided by 1 minus alpha 1 plus alpha 2. And this is our required equation in order to obtain the anode current. See here, the value of the alpha 1 and alpha 2, that is current gain value, will be very less. And now the value of the alpha will be usually very less. And by some means, if we can bring the value of alpha 1 and alpha 2 to unity, in that case, what happens? IA will become infinity. In that case, we can easily turn on the SCR. That is, we have various turn on methods, right? and the ultimate aim of the turn-on methods in order to bring the alpha 1 and alpha 2 to approach to the value of unity such that IA will become infinity and it starts conducting. And thereafter, when the load is actually connected, in that case, we can, when the load is connected, in that case, this anode current will be limited anyways. So the ultimate aim is in whatever the turn-on method you take, in order to reduce, in order to bring this value of alpha 1 plus alpha 2 to unity is the main aim. And what are the ways how we can, what is the difference between thyristor turn-on and transistor turn-on? If you see, in order to turn on the thyristor, we will actually provide the gate triggering pulse. We provide the gate triggering pulse and then turn on the thyristor such that the regenerative action will be taking place, and once it reaches the latching current, the minimum value of the on state current, in that case it remains in the on state. And whereas transistor, we just have to provide the continuous base signal such that it will remain in the on state. Coming back to the how to bring the thyristor into the off state is by providing the negative voltage from anode to cathode such that the thyristor will be turned off. Whereas coming to the transistor, if we can just withdraw the base pulse, in that case the transistor will be off. So this is the basic operational difference between the thyristor and transistor. That is all about the two transistor analogy. And now coming to the UJT triggering circuit for SCR. Here we are actually making use of a unijunction transistor in order to turn on the SCR, or in order to generate the triggering pulse required by the SCR to bring the thyristor into the on state. Here we are making use of UJT triggering circuit. We can also make use of other methods, but this is most popular when compared to that of the other methods which we have. RC, like RC triggering. In RC triggering, the power loss which will be obtained will be high. So that is the reason we are actually going for the UJT triggering circuit. And if you see here we have a rectifier, and the AC supply is actually provided for this particular circuit. And AC circuit, if you take, it has got both positive half cycle as well as negative half cycle. Is it not? So during positive half cycle, the polarities will be positive and negative, such that anode of the diode is positive with respect to cathode. That means D1 is forward biased and it acts as an on switch. Similarly, the cathode of D2 is more negative with respect to anode. That means D2 is also forward biased. And now the current conducts through this particular circuit in this direction. That is from supply to load. Since D1 is on, it starts conducting current, and then it starts conducting current flows in this direction from resistor and then through the capacitor. And during this process, which capacitor gets charged, and it will complete its path through D2 since D2 is anyways on, and it comes back to the supply in this manner. So this is how the current conducts through the circuit, during which the capacitor is actually charging. And once the capacitor reaches the peak value, and if you see here, we are making use of a voltage regulator Zener diode. And the main purpose of Zener diode is to clamp the voltage which is actually provided by this particular rectifier. Say for example, let me give you an example. Rectifier circuit, it gives about the voltage of say 5 volts, and I need only 3 volts. In that case, this particular Zener regulator, it clamps the voltage to the required voltage, so called 3 volts. And now see, from rectifier, current flows to the resistor and only 3 volts is applied now, and the capacitor is charging. Once the capacitor reaches the peak voltage, in that case, this particular UJT circuit will be turned on. Once the capacitor reaches the peak voltage, say V peak, in that case, this particular UJT will be turned on. And once the UJT is on, in that case, current starts flowing through the primary of the pulse transformer. When the current is flowing through the pulse transformer primary, it gives away the pulse to the secondary. That is nothing but it is the triggering pulse which is actually fed to the SCR. And here, this is nothing but the gate firing circuit. This is acting as the secondary is acting as a gate firing circuit. That means a gate triggering pulse, whatever the generated pulse over here in the secondary, will be applied across the gate to cathode terminal of the SCR, and thereby SCR is actually turned on. So the main aim of this UJT triggering circuit is in order to generate the triggering pulse required by the SCR or to turn on the SCR. That is the ultimate aim. And now again, during the negative half cycle, this is happening during the positive half cycle, capacitor is getting charged, UJT is turned on, and thereby it is generating the pulse such that SCR is on during the positive half cycle. And what happens during the negative half cycle? See, now the capacitor is discharged, and again we need to charge the capacitor. For that purpose, during the negative half cycle, this is negative and polarities will be positive. That is, during the negative half cycle, the polarities are like this. This is negative and this is positive. That means, see here, diode D3 as well as D4 will be forward biased, whereas D1 and D2 will be reverse biased. Now, D3 starts conducting current. And if you see, as I already told you, rectifier, if it is say giving 5 volts and if our requirement of the circuit is only 3 volts, in that case, this particular Zener regulator, it clamps the voltage to required voltage, so called 3 volts. And then this 3 volts is actually fed to the capacitor, and during negative half cycle, current flows through the circuit. And then back to the supply. This is how actually the current is conducting through the circuit during the negative half cycle. And now, during which the capacitor is getting charged. And once the capacitor has reached the peak value, as I already told you, here UJT will be turned on and it will be conducting current through the UJT in this direction. And if you see, the current is now flowing through the primary such that the secondary generated pulse will be triggering on the SCR, turning on the SCR during the negative half cycle. And that is how the cycle repeats. That is, now when the capacitor is completely charged, it is getting discharged. And once it is completely discharged, again positive half cycle will be charging the capacitor. And thereby the cycle repeats. That means if you observe here, UJT once it is turned on and other instant it is turned off. It is acting as an oscillator circuit. So that is the reason UJT, we call it as UJT relaxation oscillator circuit. And here, see, let us analyze the operation of this particular UJT triggering circuit using waveforms in detail. See, your rectifier input will be AC, and rectifier, the purpose of a rectifier, it converts AC to DC. And here it has got both positive half cycle as well as negative half cycle. Whereas output voltage is the rectified output voltage which is converted into DC. And as I told you, rectifier output will be about 5 volts. Rectifier output will be about 5 volts. And here Zener diode we are making use of in order to clamp the voltage to the required voltage, so called 3 volts. So in that case, here this is the rectified output which is being obtained, and this Zener voltage is clamping the voltage to so called 3 volts. And now once the rectified output is obtained, In that case, what happens during the positive half cycle? The capacitor has charged to this particular instant, and once it has reached so-called peak voltage, in that case capacitor gets discharged. And while capacitor is discharging, UJT is turned on. And when UJT is turned on, in that case the pulse will be generated. That is, firing pulse will be generated. And this is nothing but that particular triggering pulse which is generated in the secondary, and it acts as the triggering pulse required by the SCR. And here, this is nothing but the firing angle of the circuit. Firing angle of the circuit. So here, during which it will be off from 0 to this instant, whereas the SCR will be turned on from this instant to this instant. So this is nothing but, again, during the negative half cycle, what is happening? The capacitor is again charging, because capacitor has completely discharged during the positive half cycle. Now again during the negative half cycle, capacitor charges, and once it reaches the peak value, again it discharges, and thereby the cycle repeats. That is, during positive half cycle it charges, and during negative half cycle it gets discharged, and the cycle repeats. And if you see, this is the firing angle, and this is the required triggering pulse which is being generated, such that from this instant to this instant, actually the SCR is being turned on. And during this period, that is firing angle, here from this instant to this instant, SCR is off. There is no output voltage. Whereas here, at this particular instant, since we are providing the triggering pulse, it is turned on from this instant to this instant. That is how we are getting output voltage from this instant to this instant. We can also control the firing angle. We can vary the firing angle by varying the value of the variable resistor, as well as by adjusting the value of the capacitor. We can adjust this firing angle value, and thereby we can control the output voltage of the SCR. That is possible. And what is the advantage with this particular UJT triggering circuit? Yes, SCR can be triggered from in the range of 180 degrees. SCR can be triggered in the range of 180 degrees by controlling this particular firing angle. And now, what is the in what way it is advantage from when compared to the other circuits? We have RC circuits, right? So in what way this is advantageous when compared to that of RC triggering circuit? If you see here, electrical isolation can be provided. Electrical isolation is being provided. That is, here we are making use of a transformer, and we are making use of a UJT. What is the purpose? Why we are actually investing so much when we already have RC triggering circuit? The reason and the main advantage is it provides electrical isolation. That is, it isolates the circuit. I mean, from we have SCR and gate firing circuit. This is being isolated from the main operating circuit with the help of a transformer. That is the reason it provides required isolation. This provides required isolation for the circuit, and thereby the gate triggering circuit as well as SCR will be protected. So that is the main advantage of this particular UJT triggering circuit. And in our upcoming video, we will be seeing necessity of series connection of SCS. Thank you.